Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. All right, welcome to Happy Path Programming. We've got the Winter Tech Forum coming up here
10
in
days.
10 days in
Still time.
beautiful
if you
Crested
wanna,
Butte, Colorado.
If you want to sign up,
We're going to have a good crew this year. So.
Yeah, we've hit the magic number, critical mass number of 25, which means
Good.
That's, 4 rooms. That's, roughly 6 people a room. It obviously doesn't work out that way. It's some rooms are more popular, other rooms are smaller, but it seems like 25 is kind of a, more than 25 is even better, but 25 is kind of a magic number. So we have that, and we
lots of good conversations to come.
A lot of interesting different people coming, and we got folks from we're supporting folks from the local university. We got 2 students and 2 professors.
Nice.
And also several folks from the community who are in various phases of learning programming. So
awesome.
It should be a good.
It's going to be fun. It's going to be a good one.
So
great. Okay. Well, today we have with us Lize Raes. Did I say your name correctly? It's
almost. It's Lize. Close enough.
Okay. What's the background? Like, what's the language origin of
it's,
you and your
Flemish.
name? Flemish.
From Belgium, yes.
Okay.
Oh, okay. But you live in Switzerland.
Exactly. Since 5 years or so, I live in Switzerland, where they speak a weird form of German.
Okay.
Nice. And so I met you at a conference, and I think I've maybe seen you at a couple conferences, but you are talking about and doing some really interesting things with AI. So we've not done a whole lot of AI stuff. So it probably is a good
not
topic
actually understanding
to cover.
what's going on with the AI.
So we're going to dive into that. But before we do that, we've been kind of experimenting with this fun opener, which is something along the lines of like, how do we?
What brings you joy?
Yeah, what brings you joy? And maybe not in life. You have a baby, and so I'm sure your baby brings you lots of joy. But
and
maybe in the realm
distress,
of
I'm sure,
programming.
Yeah.
Yeah.
In programming, right?
Yeah.
Sure.
What brings you joy in the tech world of tech?
All right. I think what I like about programming most is getting things done through programming. I'm not such a fan of the act of programming and chewing on code itself, but I like that it works afterwards and that I get things done in a smart way. And I must say,
problem solved.
Yeah. And actually, yes, I do like this part where I have to think about how exactly am I going to solve it in code, because then sometimes I feel like, I'm just paid to sit on a chair and solve Rubik's cubes. That's like the feeling when I have to code.
Yeah. And then you get it solved, and that feels really good.
Mm-hmm.
And then in the realm of AI,
I liked when we originally warned you we were going to ask that question. You go, I didn't even want to be here. what tell us about that.
When I said, I'm not going to say that on the podcast.
You said, I didn't hear that part. Sorry, because that's the interesting part. Is like, how did you stumble into to this world?
I needed a job, and I'm actually an electrotechnician. That's what I studied, and I must say, like between microelectronics basically and programming, definitely microelectronics is harder to debug because you have a false contact somewhere, and it's just horrible. Like my final thesis project was a breathing sensor where I had a glass fiber around me. And then the resonance frequency would shift, I think, based on if I would breathe in and pull it under tension or not. And it was really hard to get it working. And then when I finally, on this oscilloscope, had the thing, I took a picture and I said, yes, I stepped away. Of course, this fiber broke. Then it needs to be spliced again, which takes a week. And I was like, I don't want to work in this field.
Hardware is hard.
That's how I ended up in
hard, software is soft. Yes.
Yeah.
I came from a similar background. Yeah.
Ooh, the pain.
I liked it. So.
Oh, you liked it?
Yeah. I mean, I liked it, but then I was drawn into software. I mean, software. It's like, I don't know, something intriguing about it, more magical or something. So.
I think maybe a big difference is the pace. Like it feels like like you're
Yes.
saying, like with software, you can solve a problem like relatively quickly, generally.
Yeah.
You know, like there's some hard problems that take a
Well,
long
and the
time,
rate
but
of forward movement, like we, the languages I started with, and now the ones that we've come up with, and each one solves bigger and bigger problems. So that, whereas hardware is like, yeah, it's moving forward, but not that fast, not as fast as
Becomes
software.
smaller and smaller and weirder. Yeah.
and physics gets really challenging at some
Exactly.
point. And,
When things are little,
yeah,
Mm-hmm.
yeah. And so you were doing hardware, electrical engineering stuff, and then discovered software. And
It's not entirely like that. I only very shortly worked with as a microelectronics. I worked with cochlear implants and music perception, where we would send electricity straight in people's brain.
wow,
That was cool. Then I just stayed at
that was
home for
cool.
quite a while to raise my two older daughters, and I renovated our house. That's where, some more hardware like Arduino stuff and steering pumps and dangerous things. And then I needed a proper job, and that's where I just applied to anything technical, and that's how I rolled into Java.
Huh. Wow, right into Java from Arduino's automating your home and
Is that better though?
fibers wrapped around your body and yeah. Well, that's fun.
And it's for me, understanding the hardware. It's not essential to become a software engineer, but knowing in the back of your head, you're going, okay, yeah, I know the layers and how we got up to this level.
Mhm.
And I sometimes find it useful to have that.
It's interesting. I was shocked at the beginning when I started with Java because I had a lot of C++ back there, because also for direct hardware steering, and we always had to be very scarce with our resources and really think of how we put as much as we could in one byte. And then you come into Java, and I mean, it's such a waste.
Infinite.
It shocked me.
Yes.
Uh,
I know,
Yeah.
because part of your brain is always going, oh, we can't, there's not enough resources to do this
Yeah, or
that.
like we don't need three loops. If we do it smart enough, we can have like every if condition inside one loop. And then my colleagues are like, "What are you doing?"
Well, I don't
would you do that?
understand your code.
Let the JIT optimize it.
Right, exactly. And it's one of the first things that I did is I wrote a floating point math library for an embedded system. And so every time, for a long time after that, every time I saw a floating point operation, I was going, well, that's going to be your bottleneck right there, because I know all the wheels spinning that necessary to make that happen.
You know how many ticks on the CPU those things would take?
Oh, yeah, it was
Exactly.
really hard to. I mean, that still happens a little bit. It's like, oh, that can't be efficient.
Yeah. It is such a different world, but it is helpful, I think, to understand what's actually happening under the covers. Because, then
For my brain, it was actually really useful.
yeah. But now we're just so abstracted, like you're saying. Like
But
with
I
Java,
like that. I like that too.
It is.
I feel like our job is to keep climbing up that ladder of abstraction, because we can do more and more, which
Right,
is
we
why we're talking
We
about
got pretty
AI
far
now.
right now with AI.
Oh my gosh, yeah.
I saw
wild.
this graph, like most favorite programming languages. Like last decade it was Java, then now it's Python, and next decade it's at English, and then second most popular Mandarin. Just like that.
Yeah.
Risks.
Yeah.
Be
It's
true.
going to be really interesting to see how.
I know, and
how
I
it all
have the
goes.
same problem with thinking about AI in terms of, oh, it'll help us write programs to do this thing. And sure, it can do that. But then I started thinking, well, maybe it'll just do the thing rather than having to write
Oh, okay. Well, we're going to get into agents.
That's the end. Yes.
yeah.
Let's start with.
But let's start with models. So I know nothing about how these models that I'm using actually work. Can you give us just the rundown on what is a model? How
Can
does
I
it work?
I try, because I feel like at the WinterTech Forum years ago, you and I participated in the very first AI thing, and I think we did some sort of coin flipping thing, and that changed my perspective on not just this but science at all, because and so here's the way I am currently imagining what a large language model is. It's like a giant equation like we would have had in physics, except the equation in physics, you'd go, oh, well, this is temperature and this is air resistance, this is gravity or whatever. We have all these, we can relate to them. But with the large language model, it's a huge equation. Every time you add a new piece of data, it goes, well, I could tweak this, and I'll add a few new, what do you call those things? You know,
in an AI model.
Yeah, in the AI model. But now we have term. Okay. I'll add maybe some terms. I'll tweak these terms, and now we have an equation that is billions of terms long, and but it's still a function. You put stuff in, and it gives you stuff out. It's just we can't ever understand what those terms mean. How far off am I?
Yeah, that's somehow yes. So if we're talking about neural networks, that's about what they look like. So let me start there maybe. Somehow you're gonna digitalize your input, like it could be a heat map, it can be text as we know from LLMs, it can be vision as we know from image recognition, but it can be really anything in the end that you collect and that you can transform to zeros and ones. And then you start at your input layer, which is basically your digitalized text or image or whatever. And then you have other layers after that. That's why they call deep learning. That's because it has multiple layers. And if you have a fully connected network, every node will be from one layer will be connected to every other node from the next layer. And how much of one node propagates to each of the other ones, that's a set of weights. So there's a set of weights going from the first node to all the next nodes in the next layer. Then there's a set of weight for the second node, same. And then you can have multiple layers. And at some point, you will arrive at the output that you actually want to see, which can be like yes or no, but can be a class of images, like is the dog, cat, whatever, or it's a whole text or the next word. So that's how LLMs work. Large language models will typically predict the next word and then and the next.
So back to Bruce's metaphor of the equation with the layering, is it like I've got an equation that takes some parameters, but then that's going to go to the next layer and call another equation with other parameters, and the weights are kind of directing the one equation to the next equation?
Yeah, so in its most simple form, it's rather simple. It's really like weight 1 times node 1 gives the next layer, and then weight 2 times node 1, and it's just pretty linear, but there's so many nodes, right? And then it propagates through. And as you said, it's unclear what's happening in these layers in between. Like, what do they represent? Although there are also efforts to kind of explain it. So there's the types of models where it's more clear what's happening in between. And for example, if for image recognition, the first thing you will do is send a filter through your image. So it will pass over your whole image. It's called a convolutional neural network. And it will reduce the dimensions actually. And it will notice things like edges or contrasts or texture. And then you will bring those down to what's really needed to still understand your image. So this whole black piece, for example, is gravely reduced, and then at some point comes a fully connected neural network in there, and so on and so on. So there it's a bit more understandable what's going on, but still, as you say, and the real magic, people don't talk about this enough, but the real magic is like, how do you train this? Because imagining that a huge equation, you can input any language and it will output a language that makes sense. Yes, I can imagine. Like if it's big enough, yeah. But how did you find out those weights, right? And that's the cool thing. Basically, you're gonna start at the last layer, so you're gonna have a lot of training data.
The whole internet.
For example, when you want to train on text, or when you want to train on images, it's gonna be a bunch of images, and then humans will have categorized them. And so you're gonna split it in a part that you're gonna use for training, and a part that you're going to use for testing afterwards if your trained model is actually good. Because of course, if you send in the exact same stuff and you train it on, it's a bit cheating, right? So you take apart, let's say 80% of your data set you use as training data. And then you start, I think generally these weights are pretty randomly initialized. You send the first thing through, and yeah, what comes out is complete bullshit. But then you're gonna back propagate, and they do so by making a differential equation. So they, for the last layer, one step back, they're gonna say, okay, this first node from the one but last layer contributed so much, the second node contributed so much, and then you're gonna do a differential equation, and you're gonna be able to adapt
Sorry,
the right
who's
weight.
you said they are making a differential equation. Who is they?
They is the data scientist. So,
Okay, so a
I
person
find
is
this
doing
really interesting, but also as a Java developer, you do not actually need to know or understand it. You just need to understand that the more weights and the more nodes in there, the better the result is going to be. And also that you will need a lot of parallel programming and matrix multiplications if you want to run big models. That's where the GPU comes in. That's kind of important to know once you start working with models.
Yeah. So the training side, what we're doing is we're building up the layers and the weights, the initial weights, and the layers are, I don't know, let's
The
just
layers
call them
are part of the
equations or something.
architecture. So
Okay.
you choose a bit how many layers with how many nodes, and then the weights are the thing that gets really trained by
Yeah.
data scientists.
Oh, okay.
Typically in Python, but it can be done also in Java.
Yeah. Yeah. So okay, so we've got the model, which is these layers and the weights have been the thing that we've trained. What's so then there's the equations and the layers, and then you said I think the data scientist is the one that's defining those equations essentially, or those
the differential equations.
differential equations.
I mean, yes, but it's automated, right? It's a technique to train this, and typically you have wrappers and APIs to make this really easy.
What are some of the libraries that people use for creating those?
So in Python, it would be PyTorch and TensorFlow, for example. But
Which
in
are
Java, we
both
have
written in Scala, I think.
No, those are all Python, I think.
wow, I didn't know that.
No, I think.
I don't know.
Or
research that.
Oh yeah,
Yeah, that's research.
Yeah. PyTorch is definitely Python. TensorFlow.
I mean, they are Python frameworks for sure. And then under the hood, I mean, yeah, it's Python. And then once you start running on the GPU, it often uses CUDA, which is NVIDIA's GPU accelerator framework. So you can
like
optimize your calculations.
Matrix multiplication, matrix
Exactly.
math stuff that runs on the GPU, and so it can do the
Exactly. Yeah.
big matrix stuff super fast.
Yeah.
So okay, so we take a bunch of training data, we run it through this system, PyTorch, TensorFlow, whatever, and that's going
Or
to
deep learning for J. Just wanted to say.
for J, a Java one. Awesome.
Yes.
So we could do this on the JVM if we want, but then I'm sure that it can also use the GPU in places or call it to CUDA or something. Or
yes. They have some integration with, I think, ND4J, which uses CUDA then under the hood.
Okay.
Yeah.
Some JNI.
But again, then you need NVIDIA hardware, which we typically don't. But there are some frameworks for also. I mean, I have a Mac for my M4 chip. So there are
so we
covering that.
take the training data, we run it through one of these systems, we get to the model, and the model is the equations and the weights. Like when I download a model file, what's in there?
Yeah, so either you will have an architecture in there and all the weights, and then you can run it with something that knows how to turn this information into the right equation. But there's, for example, also C++ files that are really like programs, actually. As you say, it's actually an algorithm or it's actually an equation. So you can also run it in that way.
Okay. So I get my model, and then that's been created through training and testing, and then I want to actually use it, and that's the inference side. Is that right? And so walk us through what happens with inference.
It's the same as when you train it. Basically, you send input in, it runs the whole equation or algorithm as you want, and then the output comes out, except that now it's going to be correct enough. You don't need to tweak the weights anymore. You just use it like that.
Okay. And then the weights, are the weights like immutable, or is there some way to adapt weights? Like I was using Claude and I got a bad answer and I hit like the thumbs down button. Does that update the weights in any way, or is there some other way to deal with changing the model, or adapting the model?
I don't think that when you hit the thumbs down button in Claude, it will immediately adapt the weights, but it will be used in a future training data set, probably. That's why they collect this information. Or, I mean, it can also be that a human takes a look at it and see in which way did our system actually fail. Because that's another thing. For example, large language models at the beginning, they wanted to just predict the next word that made the most sense. And they were trained on things like medical encyclopedia, and then it would just keep filling out this encyclopedia. But then people started asking it questions. But it's an encyclopedia is not like questions and answers, right? So they retrained it a bit. They may have changed the whole structure a bit. Maybe there's some stuff happening in the input before the model is actually launched, for example, to make it answer to questions rather than just spit out encyclopedic data. So that's also why they gather your feedback, especially negative feedback is interesting.
Yeah.
To see where they can improve. Or like they added a calculator at some point, I think, because the model is so bad at math, right?
Yeah. Some way to identify.
That's the stuff you get from your feedback. Or it goes into the training data set for a next upgrade.
Okay. But these are like monolithic, like massive training jobs that I've heard take, you spend millions of dollars on GPUs to do these trainings. So there's not like micro trainings that happen kind of periodically, or like are these only done in these big monolithic trainings?
I think LLMs are just static models.
No.
They don't
sorry to
please, that's my.
But you can fine-tune them.
Okay, fine-tuning.
There are some techniques where you're gonna stick to your weights mainly, and then they try to make it so as efficient as possible to just tweak a bit how the model will answer. It will never change it entirely, but you can tweak the style, for example, in which your model is gonna answer.
Okay. So that would be in the fine tuning, and you can do kind of lighter weight fine tuning of a model on top of the very large
existing one. Yeah.
But that ability also had to be added in, right? The ability to tweak wasn't. I mean, because my understanding is initially they were saying, okay, we generated the model, you can use it, and then later the models were modified so that we want to be able to tweak these things. Am I right? Wrong?
I wouldn't know. I find it very interesting, and it's possible. I know there's a whole bunch of different fine-tuning techniques, some more optimal, some less optimal, and I suppose some way it may indeed play with a certain pre-made setup of a model.
And then real quick, I want to I have two questions. One is these models often have parameters that are kind of more static parameters than the input, like temperature. There's like top P or something, top N. So anyways, there's some parameters that you can, when you make your request, like alter the behavior. Tell me a little bit about, like, I don't know, let's just say temperature.
All right. So temperature. So again, the parameters that you have depend on the model and the provider. But temperature, most models have it, and it's the higher your temperature, the more creative your model gets. So I think there's just more randomness added. Whereas the lower your temperature, it's going to be more deterministic. It's supposed to make less things up, but it can always make things up, right? It can always hallucinate, as they say. And then top K and top N, there's parameters that say like you shouldn't repeat the same word too many times, things like that.
So these parameters have been, they get used by the, let's say, equations in the model to change the behavior of
a bit,
how it's,
in certain ways.
But
and also again, depending on the model.
Can tweak.
Yeah. They become input parameters.
Okay.
And then one other quick question is, I've heard the one of the revolutions in this space was Google invented this thing called transformers. Do you know what the transformers are? It's like, I don't know. I heard it was like
No,
the
I
breakthrough.
I could try to bullshit here, but I'm gonna abstain. So I'm not a machine learning expert. I
You're
know
more
it's.
on the
I
usage.
wonder if it has to do with this attention mechanism, where they, I think add a layer in front where they kind of, oh, she was referring to this and this word goes with this, so they structure it more. But I wouldn't put my hand in the fire for this.
Okay, so let's hop back to transformers. So I think you got some insight on transformers.
Yes. So during my little breastfeeding pause, I was able to check. So it's indeed about this attention mechanism. So LLMs, to go from text, the text is first split into tokens, which typically are around 3 characters long. It's like this minimal meaningful unit for a large language model. And then those are translated into vectors typically. And so in comes this attention mechanism where all tokens are compared to all tokens, how much they are related. So as I said, like she wears her coat and she and her is very related, but also, I mean, it's also her coat. And so the most important words come to stick out, and the relationships are also encoded in this attention mechanism and this transformation.
Okay. Huh.
Yes.
And that was maybe one of the breakthroughs with LLMs, was being able to have this attention so that it doesn't just give gibberish, nonsense. It gives a much more kind of directed answer.
Yes, for sure.
And the attention mechanism was created by humans or by the machine?
I think the architecture was invented by someone at Google.
So somebody had
I think
to
it's
say,
Google, but you could argue that these people are machines at Google.
yes, but that's a whole nother level of. But I mean, somebody said, "Oh, we need an attention filter or whatever," and I'll write
Yes.
that. Okay,
But I mean, it makes sense, right? That you will not be able to interpret a phrase very well if you do not look what goes to what. Part of why they made it was also because they didn't want to process one word after the other, but they wanted to parallelize it. And so the place of the word in the sentence matters, and how they correlate when you want to throw it in all in parallel.
But doesn't that mean that, or maybe that's what you were saying before, it's like, well, that's different in different languages. And so, in other words, like if you're dealing with Italian, they put, objects have gender and stuff like that. It's
Yeah, true.
So whereas English isn't that way. So does that mean that our language models are, by happenstance, are going to be English oriented, or as you say, maybe Chinese oriented if you're...
Yeah, so it is true that you need to train a model to each language you want to use it with the whole data set in that language. I'm not sure. I would imagine certain parts of grammatics, of course, are in common. So I don't know to which point it's fine tuning, plugging in another language. It's all very interesting. But so again, I'm not the machine learning engineer. I'm more like on the inference side and what can we do with the thing.
Yeah, cool. Did you have some other questions?
Well, yeah. So I don't know if you're aware of the thing that in the 90s we had the AI revolution, which you don't remember because it fell flat on its face. But we had neural nets and other things back then. But my guess is, and maybe you can yay or nay this, is that we just didn't have the compute
and the
to
data.
Yeah, well, and the data. That's true. So those are the two things, and that's why it didn't work. Or my guess is that the marketing people were pushing it too hard, and that's what crashed and burned it as well. But it didn't go anywhere. So, yeah. So it doesn't.
I think.
I was 5 years old, so
okay.
I don't
So
know.
we won't. Let's go past that.
But I think there was a kind of a question around that, which is, we have different architectures for creating and using models, and
or
the
maybe
neural
just
net,
different models.
yeah.
Because she said architecture when she was talking about the number of layers within the neural net. So maybe it's entirely different models. So the neural net, that's a model? Is that right?
I'm not sure.
Oh, okay.
And I'm wondering, like, what I learned when I was learning speech processing was these hidden Markov models,
Oh,
which may
Markov
somehow be
chain.
related.
Yeah.
I know the phrase Markov chain, and that's it.
I think I have a much better understanding of kind of models and inference and how the stuff relates. So,
Oh, and by the way, if I can still say one thing on the topic,
Yes.
there are also much smaller models. So, like for 3 to 4 gigabytes now, you can download the weights or the model. Phi 3, Llama 3, they all have very small versions, and they're definitely not as good, but for some things they are good enough. And then you can
What
run
are
them
they
even
good
on your
for?
CPU. Sorry?
What are they good for?
For more easy things, if you want general information, yes. If you want to have them do some complex reasoning or execute some complex step, no. The bigger large language models are able to call your code when you give them your function signature and your parameters that you expect. They can say, oh, but I want to call the code, give me the answer, and then I can work on with it. And it can be done in some of these smaller models, but it's very often bullshit. So
this is some models have the ability to do like function calling or tool usage, and this is the ability for like in model execution, you're able to kind of direct the AI to then call some external thing instead of doing everything within its weights and
But
layers.
maybe this 3 or 4 megabyte, I forget, what did you say?
gigabyte.
Gigabyte. Okay, so maybe I can eventually have my dream of a vacuum cleaner that will actually work and not tumble down the stairs and all that kind of stuff.
I think that might well work.
Okay.
But there's a very nice use case of, do we need AI for this, or can you somehow in another way tell it where your stairs are?
Yeah. Well, and there's now like one of the hot things I think has been the multimodal models. So having a
Yes.
model that can understand images as well as text as well as audio, and because I think early large language models were just about text, right?
Yes.
And now it's like, oh, wouldn't it be nice if our model also understood images? And so multimodal models are now getting more capabilities, but also larger. But then in the case of like a Llama 1 billion parameter model, I think it only understands text and doesn't do function calling. And so it's much more limited. Maybe it does function calling. But.
Yeah. Okay. And also there's multimodal models, which means they're going to combine different types of inputs or outputs or both. But there's also just image models and just audio models, right? That are not, then they are not called multimodal. So multimodal is really if you throw multiple things in there or you get different things out.
Yeah, so you can have a model that only does one mode, or you can have a model that does multi-mode.
Yeah.
And then there's even more specialized models. People have created models just for programming. And so you get a model that does, if you ask it like, what's the capital of whatever, it's going to be like, I don't know. But if you're like, write this Python code for me, it's like, okay. And so it's kind of more
that's interesting.
specialized.
So I'm not sure. I know that most code models, that's a good question. I know that they are variations on LLMs.
Yeah.
Because they have much in common, right? Language and coding, it's another type of language. So
maybe it would know the capital of something, but
yeah,
it's
right.
not going
I
to
would
be as
expect.
good at kind of general knowledge as maybe one of the other models.
Yeah,
It's
I
more,
mean, I don't think they could ever, for example, Copilot could never come up with so much domain knowledge when giving your methods proper names and giving the commands if it wasn't also knowing about the capital, right?
yeah.
So I think they're LLMs that are specialized for code.
Yeah. And I'm sure many others. You can
And
go
something
into
like
Hugging
that.
Face and see all these open source
Yeah.
models.
So Hugging Face is really cool. So people can upload their models. It's like GitHub but for models, where all open source models of all kinds, right? So I've worked in drug development, and there you have completely different modes than like text and audio. You have like, oh, we have a protein sequence in, and we have a binding affinity, like how well does it bind to something else as an output, for example. So yeah, you can train models for basically everything. Also 3D images, also medical imaging, it's breast cancer detection. It's really, really cool. But again, it's a bit out of the scope of what I do. It's more data scientists that do this together with people that work in the field.
Okay, but I mean, so you're aware of the whole protein folding. We've solved that problem now, and that was the the AlphaGo people.
AlphaFold. Yes.
Yeah, the AlphaFold. Okay, so is that also using a neural network, or is that using some other kind of model?
I bet it's a neural network, but I'm not sure. But okay. I bet yes.
Because it seemed like they were doing things that everybody was going, no, I don't think that'll work. You know, it felt very different than what we've been doing. There's a video out, I think I'm pretty sure it's from Veritasium on YouTube, which is a great channel by itself. And they go into the solution of the protein, the AlphaFold stuff and where it came from and everything. And it's quite good. And they show the proteins and how they fold, and they kind of take you through that. But because it felt different, it felt like they had done something that was more than just but I don't know.
I should look into it. You know that there is Alpha Proteo now, which is like the new version, which will, I think it predicts a sequence that will fit on another one.
Well,
and that starts being drug discovery.
Is that because the Nobel Prize, I don't know, last year or whatever, was shared by the guy who was, captained the AlphaFold project, and the scientist who came up with being able to, say, I want a protein that does this thing, and could actually generate it.
Yeah. It's amazing. Yeah. I think you're going to see great progress in that field over the coming years.
It's going to be mind-blowing.
Combined with CRISPR, wow.
Yeah, it's
bioengineering. It's going to be fun.
Yeah.
Okay, so
anything
else on models?
Yeah, the models are super cool, but I think that we software developers, since we're not, I mean, you can transition into data science. It's variants of technical thinking, so we can move there. But I think there is a place for using all these models in a user-friendly way in an application, because otherwise it's like a terminal and you throw in some way the data, right? We would actually want the whole world to be able to use all these models, so they're packed in some usable application.
Yeah,
and that's where I'm more into.
Well, that's your focus
is on the using the models. So we've been asking you questions about models, and not going into your area of.
So can't you just ask the AI to what would be the best way to interface with humans?
Yeah, but yes, like, you can take a crappy website and throw a screenshot in ChatGPT or Claude or whatever you want, and say like, yeah, you're a UX expert. What would you make better? And it will come up with great improvements. So yes, like people use it to see how to best interface with humans.
Mm-hmm. And what has been your experience with figuring this out? How to best interface with humans?
Wait, how I would make my code to best?
No. I mean, I understood that you just said that your interest or focus is how to connect the AIs with people. Is that right?
It's like how to be a user of models.
Right. No, so I say just programs. That for software developers as a whole, like this question, are we out of a job and stuff? For sure, AI is helping us tremendously, and it's going to get better. But there's still like, we need to wrap the models and make them presentable to users. Which is just a whole lot of work, right? There's so many cool models out there, but then to make them actually usable for your doctor that is needing to treat the patient, make that fit in their whole workflow. Like my particular focus is on LangChain4j, which is like, how do you make the most out of large language models and let them do whatever you want, basically, because they're more than just going to predict the language that comes out. Like I said, they can call tools, which is like, I think, such a big revolution again, because they do so pretty well. If you prompt them well, and there you can build really nice things which start looking like agents.
Yeah.
That's where
Before we
I'm
get to
pretty passionate
agents,
about.
give us just a little more on LangChain for J, like what that actually is, and then the tool calling piece.
All right. So LangChain for J is a framework that makes it really easy to call LLMs from commercial providers like OpenAI. So ChatGPT is powered by GPT-4 or another of their models. You can call it via API, but then you have to construct the whole call. Or you can use LangChain for J, and then it's as easy as a POM dependency for LangChain for J OpenAI, and then you make a chat model object and you say OpenAI chat model. You give it the key and you're ready to start chatting with it. You just say model.generate and that's
A
it.
developer API to the inference.
Exactly. And then you can swap it easily because there's so many providers out there, right? Mistral, Claude, Gemini, Azure, OpenAI. And then also we also have integrations for local models with Olama that runs models that you download in a container on your own computer. JLama, which is real interference on the JVM. So that's all easily pluggable in LangChain for J. And so that's
I
why
gotta check out JLlama because I've been building a little AI thing recently, and I like spin up my Olama container, and but because I'm doing this on the JVM, I could just use JLlama maybe.
Yeah.
Didn't know that.
So that's what makes it really nice. It's just really easy to connect to all these models without having to care about their particular parameters and syntax. So you can also set in the parameters. But then we also have...
And this is actually a big deal as you're working with different models. One of the things that maybe is surprising, not surprising, is that the way that you interact with the model, if you're kind of doing it without a library, there's no standardization for how the model interaction, the inference works. Like they all use different APIs, different parameters, different structures.
Yeah.
It's evolution,
Although-
baby.
And so it's just a mess. And so LangChain for J like creates a more standard API around these things.
Yeah,
right?
exactly. Although there are quite some models adhering to OpenAI's API these days, like they're becoming a bit of a standard, but there's still so many different ones out there. And yes, for LangChain for J, they look all the same. Just their parameters are different, but then you can autocomplete the parameters. It's like a builder, and then you know which parameters are in there.
Nice.
So that's one thing.
Tools.
Wait.
Yeah. Okay, not yet.
There's maybe a couple of steps in between.
Steps before we get to tools.
Yeah. So once you make calls to an LLM, that's one thing, but these models are stateless. So as we discussed, they are just like an algorithm where stuff flows through.
It's a pure function.
So if you want to have a
maybe not
memory,
pure in that it's not deterministic, but yeah. Sorry. Good.
right? It is not deterministic. Yeah. Little side note. Absolutely. You ask it twice the same thing, and it will say give different answers typically. But so if you want to really have a chat with the model, you have to keep a memory. So that's also LangChain for J makes it really easy. As you say, all these models have different APIs. So some have names like user message, system message, or user AI, or user model, whatever. And we just have a wrapper. They're either user message from us, AI message from the model, and a system message that's like a general instruction that you can set on the model about how to behave. And then whenever you swap model, you don't have to bother with the different APIs. Yeah. So that's how you keep a memory. Important for chat applications, not for other applications, right? If it's just the one in, one out, you don't have to keep the memory. Then you may have heard about RAG, Retrieval Augmented Generation. It was all the hype. So these models, they are trained until a certain date, which is typically like half a year or a year in the past. So anything that's newer, they don't know. Anything that's specific to your business and it was not online and was not in this training data set, it doesn't know. So there, it started out with just plug documents into your question, like the right fragments, but now we have already advanced RAGs, which is much nicer. It's basically saying, yeah, your model is lacking content, so you're going to give it a couple of content retrievers. If it comes from the web, or if it comes from your SQL database, or from your documents, or from any API, it's all content. Then you're going to add to your question. So basically what's happening behind the scene there is the user asks this, there is your question. You can use these segments or fragments of text to answer. And then comes all this content. And so there are already all kind of smart ways to find the content. I don't know if you want me to dive into embedding stores and vector stores. That's a bit how to find the right part of the documents.
Yeah, there's essentially different ways to do RAG and different architectures for RAG, but yeah, I think we can. And
then,
RAG, as the name implies, is you're essentially getting the output of the function from the inference, and then you're augmenting that output, right?
It's
okay.
What goes into the model is already augmented. So instead of just your question, it's your question, and here are things you can use for your answer, and then the model knows.
Okay.
It's not rocket science.
I'd assume that RAG was just like an output transformer, but what you're saying is that the way that you get different output is to provide different input.
Yeah, exactly. So it's different from fine-tuning, where you're going to retrain the weights a bit to make it answer more like you want, but that's typically going to improve the style and not really the content. If you want to really like factual things, you want to use RAG, so you're going to send a couple of pieces of information along with your question. And then it will know how to answer correctly.
So RAG was all the hype last year, but then and it's great, and lots of important ways to use it. But
I see it as a version of a tool in the end. It is a way for the model to go fetch more information. It's a version of calling code for me. Yeah. So they put it like in the input, but I will typically wrap it in a tool. That's what I secretly do, because sometimes when in RAG you ask a question like which protein would be good to tackle this disease and what's its sequence in one go, it will like do the RAG with that information and will it will find the protein from the documents, but then to find its sequence that might be in some database, but it didn't know what the protein was at the moment that I asked the question, and then it's going to fail. So I just wrap it in a tool, because so many models manage to call tools. If you say like you have a tool to search a protein database, you have a tool to look into these scientific documents, or you have a tool to really execute anything, it will know, oh, I will first have to look into the documents to find the protein, then I will look into the protein database once I have the name, and then you solve this. So I'm just wrapping it in the tool.
And what's cool about the tools is that you don't like put into your prompt that you send to the LLM, like, okay, for this piece, call this API. You like provide the tool, and you provide like, I don't know, like a prompt or something that kind of describes what the tool does, right? And then the LLM figures out like, oh, you asked for the weather. The user said something about the weather in the prompt, and now it's determined that I'm going to use the weather tool to go out and fetch the weather, and it knows how to like find the right parameters. Like I want the weather in Crested Butte, and so it knows like Crested Butte is the thing that then needs to be passed to the tool, and so like the LLM like figures out like how to essentially when and how to call an API, which is kind of amazing.
Yes. But it sounds more magical than it is. Like, I wish I could show you right here the output of what is actually sent to the model. So the real input, because it's gonna be some header about where to go to and your key and everything, and then it's gonna be this system message, how you should behave, and then it's gonna be the first user message, the first response, the second user message. Like it's typically some JSON-like format. So it's all literally there. And then the tools, they are just provided there too. Typically, the LLM provider has a syntax in which you can just define function with a description like look up weather. And then, I mean, this one is self-explanatory, but you could add a function like looks up the weather based on the town or based on the coordinates of the town or something. And then parameter description like string town. And then you can have another description saying like it needs to be the coordinates or whatever. And so the model knows what it has available, and then it has this list to pick from, and it's smart enough to pick the right thing, which somehow is cool, but somehow is also not so impressive, right? We would also know how to pick it. It's
Right.
pretty obvious often.
But this is built into the architecture of the model. Like the architecture of the model has to know how to actually do this thing. Like if
Yes.
and so there are models that don't know how to do this, and then there.
Yes. So some models don't support tools, or function calling is the other way to say it. Yeah, because they have to make a callback. That's the thing. Like you could still tell a model, well, you have this and this and this available. Now, if you want this one, call this. And if you want the other one, say this. And then we could take care of it programmatically. You could work around, yeah. But it's nicer if the model provider has the functionality, because then the model knows how to call, and it knows how if it should do it sequentially or in parallel. It knows to wait for the output of one to go on with the other one. It's really nice.
Yeah. So we've gone through RAG tools, and then the hot new thing is agents. So give us the quick rundown on agents.
All right. So agents, they are LLMs or expanded LLMs that can both reason and act. So they will think of what they have to do, and then they will try to do it. And that will typically be using tools to do it. And then they can also typically check, is the output now what I wanted? Like if you give them a tool to check, say a coding agent, it could get your code base in RAG. You ask it to change something, it can go find where to do it. If it has the tools to make updates on your repository, it will try it. And then if it's a good agent, it will also run whatever it made, look at the terminal, what came out, and maybe, continue on it until it actually compiles and runs in a proper way.
Are agents always used in like the agentic loop, where it's like looping through until it gets to the solution or has reached some limit on how many tries? Like is that the primary use of an agent?
Agents is still very wide, and like nobody really it didn't make it to the library yet. That's like it's just specifically that. So there's like the whole spectrum of it's an LLM that can use tools, is maybe the most narrow definition, to it has a loop where it will retrigger itself until it solved it. Sometimes you can also add human in the loop, or human as a tool. I like these expressions because sometimes you want input from your user before. For example, I don't know if you heard about the cursor coding assistant. It has it now has agents, which is nice. So you see them do stuff in your code until the thing compiles. But when it wants to run things on the terminal, it will always ask your permission still to actually go on.
So it's a human in the loop. It's like, I want you to make sure I'm not going to remove some file that you're going to be upset about.
Exactly, delete repository, that kind of stuff.
And I'll put it in the show notes, but there's a really great blog post from Anthropic just in the last month or so on agent architectures, and there's a dozen different architectures that they talk about for how to build agents for different purposes, and really good read.
I imagine I will give it a look. So I've been also trying to tame agents, basically, right? Because in their easiest form, from a programmatic point of view, there's an LLM that has tools and RAG, but I mean you can see it as a tool simply, and that's it. And if you tell keep calling stuff until everything works, OpenAI's GPT-4 could already get pretty decent results, but not always entirely, right? And if the thing you tell it to do is very complex and involves many steps, I've noticed you actually rather want to wrap it into kind of state machine that's either orchestrated by you. You said like first this step, then this step, then this step, and each step can call an LLM, right? But they will have different responsibilities and different tools. But it can also be orchestrated by an LLM that knows, I have steps and other agents available. So in which order do I run them, right? If you say that they have a dozen of architectures, I'm not surprised because exactly.
Well, and in an agentic system, you could use many different models. And so one of the things I saw recently was it was like DeepSeek is really good at constructing a reason reason graph or a reason like the steps that it needs to
Yeah.
accomplish some task. But I've heard, and I don't know any of this firsthand, but heard that DeepSeek wasn't so good at some of the individual tasks that you maybe would then need to do. And so there was like this agent system that would use DeepSeek to like create the reason kind of graph, but then would use other models for specific tasks within the resolved graph, essentially. So.
Yeah, that's cool. I mean, because I also want to add there another reason for me to indeed split things in smaller steps for more confined agents that have confined scope responsibilities. Basically, there's a lot of reasons to do it, but also some things are just not that hard. Some things actually have to happen in code. Like once the LLM determined together with the customer what kind of loan they can have and whatever resources they have, but afterwards it's a calculation, right? And you don't want the model to do that at all. You want to pass it on to a next node that is going to calculate, and then pass that on maybe to a next node that's then is going to talk on with the user with your calculated number. And then there's other things like I have it a lot when I built up these agentic systems in a state machine. Is like the user was discussing something, and is he now actually ready to move on or not? And for that, I will rather train a Bayesian classifier that's much, much smaller. That is not a large language model, but it can still like determine if the answer was yes. It's a silly question, right? Because the yes is true or false in programming. But if your model asks like, do you want to continue? And the answer is like, yeah, I'd rather feel like continuing. You're like, how do you handle this, right? Yeah. And then much smaller models can do it and decide, do I go on? Do I stay?
Interesting. Yeah, so, the kind of stop conditions with a Bayesian classifier. That's cool. We've gone through all these architectures and agents. Tell us about MCP, because I this is like brand new and is just wildfire. Like MCP is the hottest thing going on.
I know.
In this space,
is the first time I've heard that. So what is it?
Okay, yeah, no, I agree. I'm part of the totally hyped people here. So MCP stands for Model Context Protocol, and it was launched by Anthropic in last November. And it's actually just open protocol to specify tools in an LLM readable format. And also have the execution part of the tool with it. And that's what makes it so cool. So I'm totally using it because I'm a lazy programmer. It means that like if I want to connect to my Google Drive, I just plug in an MCP in LangChain4j because we have an integration. And I don't have to write this whole API wrapper tool myself for accessing your Gmail. I mean, of course, it's also very dangerous and you should be careful because what you do is letting your LLM write to your Google Docs or send emails, or I just created a GitHub branch. Like my LLM created it for me and I was like, okay, I would have loved it to ask my permission first. But the cool thing is, I was waiting for this. I was like, man, I'm sure so many people want to use some tools with these LLMs, and do I really have to write them all myself? And it was holding me back. And then so when this thing came out, I was like, yes. And I think a lot of people were like that. So a lot of people open source their MCP servers, it's called.
There's now hundreds of MCP servers.
Yes, exactly. So Minecraft, anything. You just like Google GitHub MCP server Minecraft and you'll find one or more.
So MCP is essentially an API for tools. It's saying like we want to have these tools plugged into our LLM, but we need some standard interaction model.
It sounds to me like we're going from tell me how to do it to do it.
Yeah, the tools can be anything. Like you could build a tool to do whatever you want, and so the MCP server can then do whatever it wants. So, but then you need an MCP client that actually will connect to the MCP servers that you have. So the Claude Desktop does this. Some of the new IDEs like Zed is an MCP client, so you can plug in whatever servers you want. But then these tools just become a part of the LLM like system, right? You're like building this whole system of tools. using standardized components essentially.
Exactly. And so these tools are often written in different programming languages, and it doesn't matter because they will communicate over standard IO or just spin it up on a port, and then your LLM knows how to call them.
Something option as well.
Yeah.
Or I
and
think
so
they use server send events or something, but
yeah. And the cool thing is that in LangChain4j, pretty quickly some people from Quarkus wrote an integration. So now it's really just get the server here. And I mean,
Spring AI also has MCP support also.
There's an official Python SDK for MCP.
Yeah, the Python SDK is
one of
Anthropic standard ones. There's, I think TypeScript has a standard one, but now Kotlin has one. Like it just is like it's exploded. Like everything in the programming space now supports MCP.
Yeah, and I was thinking, I already see the following thing that I need very much, and I think if somebody makes a protocol for it, it might also do the same thing. It's now we have agents and they can do anything you want really easily, but what triggers them? Like, are they triggered at a certain time? Are they triggered because of a certain condition? Are they triggered because, I had a pull request on my repository or something? And I'm still wrapping my head around how to architect that.
Oh, the like invocation side. Because right now it's the invocation side is typically I send a prompt, and obviously many different ways to send a prompt. But what you're saying is, can I have an invocation model, a standardized invocation model that could be time based or some event from a webhook or whatever.
Exactly that. Yeah. Because I might want to have my model triggered when somebody made a pull request and let my LLM tell me if it's interesting to me, if I should look today, or if it can wait half a week, so it can send it to my to-do list on the right place, or already give a review or like anything. But like, it's going to be interesting when these agents are invoked at specific events.
And that example is a good segue into, I think, maybe our last question is, so let's say you do hook this agentic system backed by MCP, doing all the things you could imagine. You've got that hooked to a pull request or a GitHub repo. Are we heading in the direction where some agentic system just does all our work for us?
I would say like ideally yes, in some ways. But we're definitely not there yet, right? So let's say we can see how these agents work by using a tool like Cursor, which is a code assistant, but like a really good one. I mean, the best one I've seen so far. They now just added agents. So instead of they went through your code base in a really smart way before already and gave really good suggestions. But now an agent checks if it actually compiles and tries to run it and everything. As long as that's not perfect, like whatever hook you're going to place into it is also not going to be perfect, but it is moving fast and it's getting good.
And there's a number of these now agentic IDE plugin kind of things coming out. So I think Zed has an agentic loop in it. I think Windsurf has one. I work at AWS, and so we've got the Q Developer agentic loop, which I've used and works pretty good. JetBrains now has Junie, which is in private preview. I used Junie and was pretty impressed by it, especially the way it was integrated into IntelliJ. So lots of different options emerging. I'm sure there's tens more of these systems, but it's moving quick. But we're in a year or 2 years, like what do I do if the agent just does everything for me?
You'll figure it out.
Well, it is an interesting question, but also from our home proof of concepts things to our work floor, where we're in this huge code base where everything is super sensitive, and then we typically cannot even call OpenAI because the code is IP. It's gonna lag, right? But I mean, after podcast, we should talk. I want to hear your experiences. I'm always very curious what people use and how well it works for them and where they see it evolve.
Yeah, we'll talk about that. We'll talk about it at DevNexus. When I see you there in person soon. But it's fascinating how the space is changing. At least you have electrical engineering to go back to, because it'd be hard to imagine an agent, wrapping a piece of fiber around your body and sensing your breathing.
Yeah, I don't know. I've seen this a bunch of times
robotics
before, though. Yeah, well, yeah, but but robotics will also be. But the thing is, every time we come up with a technology, everybody panics and they go, "We're all out of a job."
Compilers.
Right. Compilers is a perfect example. You probably might have written assembly language for what you did. I did.
Yep.
And then it's like compilers came along and the assembly language programmers panicked because they go, "Oh, no, my job is being done now." But all it did was allow us to increase our scale. And what we will do is we will make things with the tools that we have created. I mean, that's
so
what we're
maybe
doing
I'll
now.
be able to finish the 100 side projects that I have going on.
Yeah.
For example.
Yes. Let AI take care of that.
Right. Well,
But
and I find there are things that I'm able to do that I did not have the emotional energy or whatever capacity to do, but it'd be nice to have this, but it's gonna be too much work.
Yeah.
But now I can go, how would I do that? And I am able to, I mean, sometimes it's funny, silly little things like just tuning my desktop or whatever, but I wouldn't have done it before. But now I have this tool. I mean, I have a power tool rather than a hand wrench.
Yeah.
And so I'm able to build bigger things. And that's what we'll do. I mean, for example, one of our biggest issues is how do we house people? And we have this super dumb, old, expensive way of building houses with sticks and hammers, and the architects can only hold 7 plus or minus 2 things in their heads when they're designing it, and there are hundreds or thousands. How do you design a perfect house taking into account every factor? Architects are mostly looking, oh, how's it look? And then everything else is like an AI can say, we'll design it this way. It'll be optimally heat, it'll deal with heat. We can make it whatever cost, all these dials. And then.
So you're aiming for the AIs to replace architects.
Oh, for sure. Architects
I hear
are.
some frustration there.
Well, or anybody who's limited. I mean, anybody who's had, experience with the medical system, and you go, oh, here's this thing that if I went to the right doctor, they saw it right away. But all the other doctors, it's just over their head. And it's like, this is a thing. I mean, humans can't deal with problems of this scale. And
I agree. But
yeah,
hey, did you know that Google has this Amy, but it was a research project, and I don't know if it's gotten used in real life, but it outperformed doctors in diagnosis and even in
course.
empathy.
Even in empathy.
Oh, of
Yeah.
course.
They don't have bad days, right?
Yeah, it's like because like the one for skin cancer. If your doctor isn't using a machine to check for skin cancer, that they're not going to be doing a good job
Yeah.
because the machines do a much better job, and that's just a little thing.
I admit
now you want to replace doctors. Wow.
Well, not replace. No, but it makes it easier. We don't have enough doctors, but it'll make it easier for somebody who can become a nurse practitioner or physician's assistant plus the AI, and they're going to do a way better job. And the doctors themselves will be feeding the data to the AI. That they will be doing research and not, trying to guess what's going on.
I also see so many ways in which it can make the world better because, as you say, we don't have enough doctors. And if you, again, make a nice application, and there's an important user part to that, right? For people to actually be able to use it and to not abuse it too much because it's still health, right? This can make health so much more affordable for everybody. But it's the same for education. Like, there's huge potential.
And therapy.
Yeah.
We will never have enough therapists, and they're always going to be too expensive. And
we programmed a couple therapists with my partner just because, sometimes you need one.
Oh, yeah. Well, yeah. So here's an example. My friend from college was the city attorney for Las Vegas for 30 years. One of the things that he and other city attorneys tried to do was figure out how do we solve the homeless problem. And lots of experiments have been gone on. And he says I think there were 2 cities that had most successful experiments, which were ultimately the conclusion that they came up with is each homeless person needed their own therapist every day. It's like
Mm.
way too expensive. But if your therapist is on this,
Yeah.
you can access it whenever you run into
And by this you meant your phone.
the phone,
For those
of course.
listening.
Yeah.
Yeah.
And you integrate it with your diary, right? I mean, I have so many business ideas. One is like, oh yeah, the AI diary that gives you like prompt based on what happened or helps you through a difficult situation and makes your overall mental profile and so much
and
stuff.
the AIs will be able to have. So here's what I think will happen is that we'll move up a level, and you will have an idea, and you'll say, can I develop this? Can I start a business? And instead of you having to learn about all the business stuff or whatever, it can do that. I think it'll replace CEOs because they do terrible jobs of running businesses. And
So
benefit.
we need the
You'd rather
AI
be
to
managed
help
by
you with
an AI.
marketing.
Beg your pardon?
You'd rather be managed by an AI than by a human?
I trust. Yeah, I mean, I spent a bunch of time studying business, trying to solve the business problem, how making work not suck, and all I found was a whole bunch of myths that are propagated by business schools and business management
Yes.
consultants and everything. It's all fabricated, and I want a science machine to look at it and say, hey. Work from home actually makes the company more money. Let's do that, and not, oh no, everybody has to come back to the office because
I agree.
of other factors that have nothing to do
I
with
think we
making
can
it.
fine tune a model that just outputs that work from home is the best, and then we can go.
Yeah.
Yes, so I think we will be able to do bigger things because of our tools, and it's not going to be the job you had before, but I think it'll be a better job.
And we'll hopefully reduce the things that we're not good at or don't want to do. Like you don't like doing marketing and maybe aren't that good at it. So can we just let the AI do the marketing for us?
Are you saying you're good at marketing?
No.
You as a general person.
No, you.
Yes.
You don't like
Me
doing
personally,
marketing.
I don't, but
Yeah.
you don't either.
Right. Oh yeah. I
Yeah,
don't. Yeah.
so-
if
so
I
we-
can just have the AI do marketing for me,
Sure.
Yep.
And it'll just talk to the other AIs, and it'll find the people who actually want the thing, and
Yep.
yeah, yes, oh right, and eliminate advertising altogether, the whole advertising business, because my personal AI will talk to, I'll say, I need a new desk, and it'll go, okay, I know you, I know what you need, I will find the desk for you, you don't have to do any shopping, and it'll talk to the other AIs, and it'll figure it out, and then go, and the desk will show up,
and then I'll show up.
Amen to that.
It's the
and
future.
it'll have wheels on it this time.
Because it would know that you
It knows
want
that I
that
want
you
wheels,
need
that I
wheels.
want
Yeah.
to. It knows
That
what I
would be
want to
best
do,
for you.
and it'll give me even better recommendations than I could get by days or months of shopping. So,
Well, the future looks bright.
but I'm an optimist. So,
All right. Well, we've kept you long enough, but I really appreciate your sharing your insights with us and teaching us all about AI stuff. That was super fun.
well, not all, but as much as you could.
All right.
Apparently there's
Thank you
more.
very much for having me. Thank you very much for sharing the ideas at the end. Like I got so many more. We should.
Oh, excellent. Excellent.
Awesome. Well,
All
I'll
right,
see you at
yeah.
DevNexus. And
Yeah.
All
All right.
It was
Thank
great.
you. Bye.
Bye.